Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 4, Harmonic Constructions and the Fundamental Theorem of Projective Geometry. Section 34, Nets of Rationality in Space. Definition: a point is said to be rationally related to two planar nets, r1 squared, r2 squared, in different planes, but having a linear net in common, provided it is the intersection of two lines, each of which joins a point of r1 squared to a distinct point of r2 squared. A line is said to be rationally related to r1 squared, r2 squared if it joins two, a plane if it joins three points which are rationally related to them. The set of all points, lines, and planes rationally related to r1 squared, r2 squared is called the net of rationality in space, or of three dimensions, determined by r1 squared, r2 squared. It is also called the spatial net, defined by r1 squared, r2 squared. Theorems analogous to those derived for planar nets may now be derived for nets of rationality in space. We note first that every point of r1 squared and of r2 squared is a point of the spatial net r cubed defined by r1 squared, r2 squared. The definition applies equally well to the points of the linear net common to r1 squared, r2 squared, and that no other points of the planes of these planar nets are points of r cubed. The proofs of the fundamental theorems of alignment, etc., for spatial nets can, for the most part, be readily reduced to theorems concerning planar nets. We note first, lemma: any line joining a point a1 of r1 squared to a distinct point p of r cubed meets r2 squared. Assumption ane. Proof: by hypothesis, through p pass two lines, each of which joins a point of r1 squared to a distinct point of r2 squared. We may assume these lines distinct from the line PA1. Since otherwise the lemma is proved, let the two lines through P meet r1 squared, r2 squared in B1, B2, and C1, C2 respectively. Figure 40. If A1, B1, C1 are not collinear, the planes PA1, B1, and PA1, C1 meet r1 squared in the lines a1, b1, and a1, c1 respectively, which meet the linear net common to r1 squared, r2 squared in 2 points st respectively. Theorems 11 and 12. The same planes meet the plane of r2 squared in the lines sb2 and tc2 respectively, which are lines of r2 squared, since st are points of r2 squared. These lines meet in a point a2 of r2 squared by Theorem 11, which is evidently the point in which the line PA1 meets the plane of r2 squared. If a1, b1, c1 are collinear, let a2 be the intersection of PA1 with the plane of r2 squared, and s the intersection of a1, b1 with the linear net common to r1 squared and r2 squared. Since A1 is in R of SB1C1, the perspectivity SC1B1A1 perspective with center P to SC2B2A2 implies that A2 is in R of SB2C2, and hence in R2 squared. Theorem 13. Any line of the spatial net R cubed defined by R1 squared, R2 squared meets R1 squared and R2 squared. Assumptions A and E. Proof: by definition, the given line L contains 2 points A and B of the net R cubed. Figure 41. If A or B is on R1 squared or R2 squared, the theorem reduces to the lemma. If not, let P1 be a point of R1 squared and A2 and B2 the points in which, by the lemma, P1A and P1B meet R2 squared. Also, let P1 prime be any point of R1 squared not in the plane P1AB, and let P1 prime A and P1 prime B meet R2 squared in A2 prime and B2 prime. The lines A2, B2, and A2 prime, B2 prime meet in a point of R2 squared, Theorem 11. And this point is the point of intersection of L with the plane of R2 squared. The argument is now reduced to the case considered in the lemma. Theorem 14. The points of a spatial net lying on a line of the spatial net form a linear net. Assumptions A and E. Proof. Let L be the given line, R1 squared and R2 squared, the planar nets defining the spatial net R cubed, and L1, L2, the points in which, by Theorem 13, L meets R1 squared and R2 squared. Points L1 and L2 may coincide. Let A1 be any point of R1 squared not on L or on R2 squared, and S the point in which A1, L1 meets the linear net common to R1 squared and R2 squared. Figure 42. If L1 and L2 are distinct, the lines SL1 and SL2 meet R1 squared and R2 squared in linear nets by Theorem 12. And by Theorem 13, a line joining any point P of R cubed on L to A1 meets each of these linear nets. Hence, all points of R cubed on L are in the planar net determined by these two linear nets. Moreover, by the definition of R cubed, all the points of the projection from A1 of the linear net on SL2 upon L are points of R cubed. Hence, the points of R cubed on L are a linear net. If L1 equal L2 equal S, then, by definition, there is on L a point A of R cubed, and the line AA1 meets R2 squared in a point A2, figure 43. The lines SA1 and SA2 meet R1 squared and R2 squared in linear nets R1 and R2 by Theorem 12. If B1 is any point of R1 other than A1, the line AB1 meets R2 squared in a point B2 by Theorem 13. By Theorem 12, all points of L in the planar net determined by R1 and R2 form a linear net, and they obviously belong to R cubed. Moreover, any point of R cubed on L, when joined to A1, meets R2 squared by Theorem 13, and hence belongs to the planar net determined by R1 and R2. Hence, in this case also, the points of R cubed on L constitute a linear net. Theorem 15. The points and lines of a spatial net R cubed, which lie on a plane alpha of the net, form a planar net. Assumptions A and E. Proof. By definition, alpha contains three noncollinear points, A, B, C, of R cubed. These three lines, AB, BC, CA, meet the planar nets R1 squared and R2 squared, which determine R cubed, in points of two linear nets R1 and R2, consisting entirely of points of R cubed. These linear nets, if distinct, determine a planar net R squared of alpha, which by Theorem 10 consists entirely of points and lines of R cubed. Moreover, any line joining a point of R cubed in alpha to A or B or C must, by Theorem 13, meet R1 and R2, and hence be in R2. Hence, all points and lines of R cubed on alpha are points and lines of R squared. This completes the proof, except in the case R1 equal to R2, which case is left as an exercise. Corollary 1. A net of rationality in space is a space satisfying assumptions A and E if line can be interpreted as linear net and plane as planar net. Assumptions A and E. For all assumptions A and E except A3 are evidently satisfied, and A3 is satisfied because there is a planar net of points through any 3 points of a spatial net R cubed, and any 2 linear nets of this planar net have a point in common. This corollary establishes at once all the theorems of alignment in a net of rationality in space which are proved in Chapter 1, as also the principle of duality. We conclude then, for example, that 2 planes of a spatial net meet in a line of the net, and that 3 planes of a spatial net meet in a point of the net, if they do not meet in a line, etc. Moreover, we have at once the following corollary. Corollary 2. A spatial net is determined by any 2 of its planar nets. Assumptions A and E.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.